Let's start the 10th lecture. We will talk about clustering. Uh, we have been talking about classification so far, but today I will introduce something called clustering. First, I will talk about how classification and clustering are different. Then I will introduce clustering methods, which are the k-means method and uh, well, hierarchical clustering. In hierarchical clustering, we need to measure closeness between clusters. So I will talk about what methods there are for this and how to read dendrograms that appear in these methods. Now let's introduce what clustering is. To what we want to do is in clustering is to group data. Clustering refers to grouping data points that are similar to each other. For example, if we have customer data, we can find customer groups with similar characteristics based on that data. By doing this, if people in one group are buying a certain product, we can understand that other customers with similar characteristics in the same group might also buy that product. Also, we can group images with similar pattern based on image data, group genes with similar features based on gene data, or group documents with similar content based on text data. If we group document with similar content based on text data, we might be able to make classifications, or we might find out the same person was actually writing them. Until now, we have covered classification methods such as logistic regression, support vector machines, k-nearest neighbors, and decision trees. Classification is a method that learn using labeled data. The goal is to predict which class new data belongs to. For example, we have been distinguish whether an email is spam or not, or distinguish whether an image is a cat or a dog. On the other hand, clustering is a method that groups data using unlabeled data. The goal is to find structure or patterns in data. So, what do we think about? Let's say we have unlabeled data like this. Uh, we think about grouping this into three groups. We can clearly see that there is one separate group on the right side. If we look carefully, we might think that the left side can also be divided into top and bottom parts. By actually applying the k-means method, we can group them into red, green, and blue clusters like cluster 0, cluster 1, and cluster 2. What we want to do in clustering is to group similar things that are gathered together into one group from unlabeled data like this. Now let me quickly explain how to do this k-means method. The basic algorithm of the k-means method is as follows. let's say data is given and the number of cluster is also given. What we get the cluster assignment and cluster centered mu1 through mu k. How do we do this? First, we randomly assign clusters to each data point. We randomly assign clusters to each data. Then, let's see J be the set of data points belong to each cluster J. We take the mean of those data points. We can also say we find the center of gravity. For each cluster, we can calculate the mean at the time. Next, we calculate the distance between each data point and the obtained center of gravity. If the center of gravity mu z to mu z well here, so mu z2 is close to xi, we assign xi to cluster J. We repeat this. When the location of this center of gravity doesn't change, or when the maximum number of iteration is reached, we end the calculation. Otherwise, we repeat step to 1 and to 2. To put it simply, this is a method that just repeats calculating the mean of the data point in cluster J and assigning data points close to the center of gravity to the cluster. You probably don't understand well just from this explanation, so let's try it specifically. First, we randomly, uh, yeah, so we randomly assign clusters. We assign data to red, green, and blue. Then we can find the mean. So let's calculate the mean. We calculate the mean of three clusters, red, green, and blue. The next, we check which of red, green, and blue means is closest to each data point. In this case, all the data on the right side uh, has a red center of gravity close to it. So in the next step, it will be classified as red. For data like this, so for data like this, if green seems close, uh, so it will be classified as green. The other parts, so these parts, uh, are closer to blue, so they will be classified as blue. This happened in one step. Uh, since the assignment has changed again, we find the mean again for each red, green, blue. Then x max becomes the mean. Again, we check which is closest to each data point. The red center of gravity, so the red center of gravity, the green center of gravity, the blue center of gravity. The red part doesn't change, but since the assignment of the green and blue part, so around here, is closest to green, so become like this. The data in upper left part is closer to green, then it gets assigned to green. Since it become like this, let's find the mean again. Then the mean of green and the blue become like this. The part of the blue is closer to the mean of the green center of gravity, so that area becomes green, like this. By repeating this, we finally get the green, blue classification like we saw in area. So this one. The implementation of k-means method itself is straightforward. First, here, so first we randomly assign data and calculate here. So calculate the center for each cluster. If there is no data, we set it to infinity, which means we set it to be very far away, so it gets ignored. Then for each data point, uh, we calculate which cluster center is close. So this part. We update the cluster level of that sample to the cluster with the closest distance. By repeating such things, we implement the algorithm with the area. If we write it with scikit-learn, it looks like this. I suddenly introduced the algorithm, but let me talk about what the k-means method is basically doing. Uh, the problem being solved is this. When data is given, there is a set defined by center of gravity mu1 through mu k, and we calculate the distance between that and that data points. That is the distance to the center for each cluster. And we want to find mu1 through mu k that minimize the sum of all those distance. That Cj is the set of data points for which mu j is closest among mu1 through mu k. Please think of it as this kind of problem. This itself is known to be a very difficult problem. So the k-means method is a technique for finding a local solution to this problem. Of course, as you can guess, when we randomly assign at the beginning, we talked about wanting to minimize the cost earlier, but this area doesn't always give us good solution. In fact, the result varies depending on the initial cluster assignment. So it's better to repeat it several times. The good points of the K-means method are that it is simple to implement and computationally inexpensive. In scikit-learn, it is the fastest method among clustering techniques. Because computational cost is low, it is applicable to large-scale dataset. Also, clustering results are intuitively understandable. The disadvantage is that the number of cluster K needs to be specified in advance. It's generally difficult to know how many groups the data has. So there is a problem that you have to specify this. Also, as I introduced earlier, it is prone to local optima and sensitive to initial values. Also, the shape of the clusters you get tends to be spherical. That means if it's two-dimensional, it becomes circular. It tends to become circular. Moreover, since clusters of the same size tend to be obtained, uh, it's difficult to extract clusters with extreme shapes. It is also sensitive to outliers and noise. Furthermore, it is depend on the scale of the data, that is, the size of each feature. This is the same as the k-nearest neighbor method. Since we calculate distance, it depends on the size of each feature. So, standardization or normalization is necessary. This was the k-mean method. Okay, next we'll talk about clustering. But I will also to so okay, let's move on to hierarchical clustering next. The algorithm of hierarchical clustering is that data is given and what we get a cluster assignment. The calculation method is to first treat each data point as separate cluster. That means if there are n data points, we think there are n clusters. Then we find the closest clusters and merge them. If they are close data points, we make them into one cluster. Next, we merge the close cluster again. Then eventually everything becomes one, but we repeat this until it becomes one. Hierarchical clustering is a method that initial treats all data points as separate clusters, sequentially merges cross one, and eventually combines them into a single cluster. What is meant to by close will be discussed later. Let's actually see how we do this. Let's let's group the Laravel data into three data. At first, we separate everything. First, if there are close data points, although we will discuss later what we mean by close, we group them into the same cluster like this. In the next step, if the here, if the red and the purple uh, here are judged to be close, we combine them into one cluster. Like this. And finally, there are only these two, so this becomes one cluster. This is a method where clusters gradually come together step by step. This is about what we mean by close. We have been learning about the distance between two points since elementary school. Representative example is Euclidean distance. So how do we measure the closeness between sets of data? This is not uniquely determined, and various methods have been considered. Let me introduce them one by one. First, it is a single linkage method, which is the simplest. The single linkage method defines the closeness between the two clusters A and B as distance between the closest data point between the clusters. That means we take data from cluster A and B and find the distance. We use the closest distance as distance between those clusters. This is the single linkage method. Since it uses the closest distance, it is also called the minimal distance method. This is easy to understand, but it tends to create large clusters. And there is also effect called the chain effect, which tends to produce elongate cluster. Actually, if we proceed with this figure, the closest is green. They were grouped into green. Uh, okay, so next, which point is so next we point which point is closest? This point seems to be close, so it become orange. What's close to this is apparently green, so it become orange and everything. Uh, Finally, everything become orange. In this way, we can confirm the tendency for large clusters to form. In other words, since clusters take in the closest ones, once a large one is formed, like that, so there is a high probability that the closest one will be there, so it gets taken in. Next is something called the complete linkage method. Earlier, we choose the closest one, but the complete linkage method defines the closeness between two clusters A and B as distance between the furthest data point between the clusters. Since it uses the furthest data, it is also called the maximum distance method. Unlike the single linked method earlier, it tends to create clusters of similar size rather than large clusters. The changing effect from earlier does not occur. Actually, doing this look like this, as you can see that there is tendency for clusters of similar size to form. This is the opposite of earlier. Since we take the distance of the furthest data between clusters, when data cluster become larger, uh, when we measure distance between data, the furthest place in the cluster is adapted as the distance, so that cluster becomes difficult to grow. This is why clusters of similar size tend to form. There is another method. There is something called the group average method. The group average method defines the closeness between two clusters A and B as average distance between all data points in the cluster. This absolute So this absolute value of A represents the number of data points, not the absolute value. So it is known to produce clusters intermediate between single linkage and complete linkage. When we try the same example as before in single linkage method, one large cluster kept growing, but that's not the case here. We can see that clusters different from uh, both single linkage and complete linkage are formed. It's especially clear when the number of clusters is 3. Next is word method. A word method defines the closeness between two cluster A and B as the increase in within cluster variance when the clusters are merged. This mu is the mean of the cluster. We calculate the sum of squared distance from the mean when A and B are combined, then subtract the sum of square distance from data in A to the mean of A, and the sum of square distance from data in B to the mean of B. This is also called the minimal variance method. It is known to be robust to outliers and practically useful, so it is often used. On the other hand, it has the property that the spherical clusters tend to appear. In this example, results similar to complete linkage was obtained, but as I will discuss later, different results are often obtained as well. When we compare each method, it looks like this. On the far left is a single linkage method. Second from the left is group average method. Second from the right is complete linkage method. And on the far right is word method. Single linkage perform well on non-spherical data, but its perform degrees in presence of noise. Also, large group tend to formally easily as you can see from this. Group average and complete linkage uh, work well on cleanly separated spherical data, but produce mixed results otherwise. Ward's method works well even the noisy data, like the start of the top of case like this. In addition to the methods introduced so far, there are also the centroid method and median method. The centroid method defined the closeness between two clusters as the distance between their centroids, and the median method defined the closeness between two clusters as distance between their medians. The median is usually determined in one dimension. So, more precisely, two. So here, this one. We calculate the median of each dimension and treat the array of these medians as the cluster's median. Also, we have been using Euclidean distance as the distance, but we sometimes also L1 distance, also called Manhattan distance. Minkowski distance, which generalize these, and cosine similarity. Anyway, we are considering the case of Euclidean distance, but when we implement this Python, it looks like this. The Python implementation of hierarchical clustering first initialize case we speak uh, so first initialize each data point separate cluster, and also create a list to store the clustering result. We repeat cluster merged for n clusters to one cluster. First, we initialize the distance to infinity, and for each cluster, we measure the distance between the I minus ith uh, cluster and jth cluster. Since we specify which method to use at the beginning of the function, we measure the distance between x and y using that specified distance. As usually similar to the method of finding the minimum value, we search for minimum distance and look for the cluster pair with minimum distance. When the search is finished, we match the cluster pair with minimum distance. We repeat clustering like this. With scikit-1, it looks like this. Okay, let's take a break. Okay, let's restart. To see how these are connected, something called a dendrogram is used. A dendrogram is a diagram showing the process of hierarchical clustering. It represents the merging of cluster as a tree. The leaves, the leaves of the bottom of the dendrogram, so this part, these represent individual data points. For example, in this figure, each leaf represents the data points from 0 to 5. And these branches indicate the uh, merging of clusters. For example, that means in this case, 2 and 3 merge first, then 0 and 1 and 4 and 5 merge at about the same timing. Then the cluster of 0 and 1, so in this case 0 and 1, and the cluster 2 and 3 merge. And finally, everything becomes 1. The vertical axis of the dendrogram represents the merging distance between clusters. This means that the higher the position at which clusters are merged, the larger the distance between them. If we read the previous figure properly, in this diagram, data points 2 and 3 merged first. The height of the merge is about 2, so we can see that the distance between these points using Wall's method, Wall's method, uh, is about 2. Finally, the two large clusters, the cluster of 0, 1, 2, and 3, and the cluster of 4 and 5 are merged. The height of this merge is about 5.5. This is the maximum height, indicating that the distance between these clusters is the largest. If we look at the previous figure again, so it corresponds like this. No, here, like this. We can determine the number of clusters using dendrogram. It becomes the basis for a decision. The key to the decision is the point in dendrogram where the distance to the next clustering starts to become longer. So like that, and like that. A long distance until clustering can be interrupted, the cluster being far apart. For example, if a horizontal line is drawn around height of 4.5 in the dendrogram, the clusters are divided into two. They are divided into the cluster of 0 or 1 to 3 and the cluster of 4 and 5. In this case, the distance from uh, having three clusters to becoming two cluster is long, so this part. Also, the distance from two clusters become one cluster is also long. So we can estimate that it would be good to divide into 2 or 3 cluster. Of course, looking at the timing of merging, there could be 6 cases, but that wouldn't form clusters in the first place, so it'd be meaningless. Okay, the figure below shows the dendrogram for each method. We can see that the single linkage method produces largest clusters. One complete linkage and word method for form all data into some clusters at lower height compared to simple linkage. Hierarchical clustering can represent the clustering process that leads at the tree structure with dendrogram. So we can visually confirm how data is merged into clusters. Also, no need to specify the number of clusters in advance is a good point. Also, Ward's method is known to be relatively robust to outliers. K-means method K-means is classified as non-hierarchical clustering because the hierarchical structure is not visible, but K-means needs to determine the number of clusters in advance. However, since it can be calculated at high speed, K-means is more suitable for large-scale dataset. The explanation is like this. Now let's talk about the code. Hey, now let's look at the implementation for the k-means method first. Let's prepare the library as usually. Let's prepare for data generation. Uh, so here we generate data three clusters. We create a scatter plot centered around cluster 1's center coordinate to 0. Uh, Cluster second's center coordinates -1, 2. And cluster 3 third's center coordinate -2. And combine them to make the data. Earlier, it divided into three parts, but that wasn't by chance. We were creating that kind of data. The k-means method is as I introduced earlier. First, we initialize uh, an array to store cluster centers and randomly assign sample to initial clusters. In the loop, so this loop, in the loop, we calculate the center of each cluster. This part here. If there are no sample in the cluster, we set it to infinity. By setting it to infinity, it's extremely far away, so nothing gets assigned there. Next, for each data point, we set the minimum distance to infinity and run a program to find the minimum value. When it becomes a minimum value, that is when it becomes a closest coordinate, we update the cluster of the sample. That means when it's closer to the case cluster center, we update the label to K. When data is given like this, and we specify the number of the clusters and estimate clusters with the k-means method, for example, if we want to see which cluster or the third uh, data point was assigned, we can look at level 3. When we plot with different colors for each cluster, it looks like this. For implementation with scikit-learn, if we use k-mean here, k-means, and write like this, we can get a similar result. Of course, they don't match completely like here. Here, it's different. And depending on initial values, different classification results may occur. This is due to the characteristics that the k-means method depends on random initial values. Next is hierarchical clustering. There are various distances. The calculation methods are like this now. Oh. This part is quite complicated, so it's fine to understand that this is how we can calculate it. For words methods, there are also more efficient calculation method, but we are using the simplest approach. The implementation of the hierarchical clustering initialize here. Each data point as a separate cluster. First, initialize the minimal distance to infinity and calculate the distance between each cluster. So this part. Oh. This is a program that search for one with a minimal distance. We remember which combination was cluster pair with minimal distance, and when this processing is finished, we merge the cluster pair with minimal distance. If we look at the content of this, well, ah, okay. Here. Okay, let's go. So if we look at the content of this, the contents look like this. But looking at the example, we can't immediately see which clusters merge at which timing. So we use get cluster assignment to specify the number of clusters and check which cluster was assigned when we have the specified number of clusters. We prepare data like this, executing hierarchical clustering. And when we want to know the second data point, when the number of cluster is 3, we write it like this. Then when we can confirm which cluster it was assigned, uh, that it was assigned to cluster 1. When we visualize clustering, we can see that it looks like this. Come on, minus here. The result of clustering with different distance look like this. With single linkage, we can see that large clusters are formed. And with complete linkage, we can confirm the cluster of similar size tend to form. We can also implement with scikit-learn. We need to define function called plot diagram, dendrogram, but we can draw dendrogram. This is just about how it can be done normally. So it was look like this. Okay. Look like this. This is I have so I so this is these are slide figures. Okay, so let's try the in-class report. So about today's in-class report, here. First, there are questions about what properties it has in text. And then there are problems where we actually apply it to data. In this case, the problem is to confirm the cluster assigned to the fourth, sixth, and ninth data points and choose the most appropriate one from the following choice here. That means, as we confirmed earlier, well, here. We can check which cluster is assigned like this. So if we confirm which clusters that fourth, sixth, and ninth are assigned to respectively, the problem can be solved. It's a calculation problem, and after that, it becomes similar problem for so theoretical clustering. Okay, that's all.